In the last lecture, I described the understanding of a quantum chaos. In brief, it boils down to the fact that quantum states are distributions described by pairs of conjugate variables, and the smearing which comes with that suppresses chaos by removing small scale fluctuations. So now to see how it works in practice, I gave the problem to one of my former students, Ankit, to see the behavior of this quantum chaos in a specific example. And that example belongs to what is called the classification problem. And first I will give a general description of what this problem is. It is a particular situation which is common in many instances of what is called machine learning. And then we'll go back to see how the problem of quantum chaos can be studied in this particular example. So this is a problem in what is called supervised machine learning, and the area of application is basically analysis of big data, and big means there is no time or space to store it. It comes, you can extract whatever you want from it and then let it go. If you don't have the means to learn anything as the data is coming, well, you can't gain anything out of it. So it's use it or lose it kind of situation. And the computer language is its online analysis. Examples are all over the place, and I will just illustrate the wide variety. Probably the oldest one belongs to astronomy. The signals are coming all the time. If you can extract something out of it, you can learn something. Otherwise, even when humans were not there on this planet, the signals were coming, nobody learned anything. So that is the situation. And then the modern versions of this is area of image processing and surveillance. Huge amount of stuff is collected. If anybody can learn anything from it, it is fine. Otherwise, it just gets deleted. And yeah, this is now used in all kind of situation. Probably the familiar one is the face recognition. But yes, you have to deal with those kind of situation. It doesn't stop at this stage. There is also examples for particle physics, where you have this large amount of collider data coming in. You want to look for some signatures. If you succeed, fine. Otherwise, the data is just thrown away. And of course, it goes all over the place. The large databases. There in biology also, huge amount of information is there. Where you can find something from it or not, that is up to you. So, no doubt about the situations in which these problems occur. The question is, how do you deal with this kind of situation? And here comes the strategy of this classification problem. What it does is reduces this data analysis to a structure which we are familiar with it, which is the binary tree. It's the same thing which we use when you look up a word in a dictionary. Okay? Break up the signature of whatever you are looking for in a set of binary question, and then go down the tree, yes, no, etc., like looking for one letter in the word one by one till you find what you are looking for. And the advantage is that with n such binary questions, you can look up 2 to the n possibilities. Okay. So, and this is what is implemented in lots of machine learning algorithms. Binary search is a familiar example, and that means at every stage you have to take one particular sample from the data and ask a yes or no question. So, these binary questions are addressed by linear classifier, which basically means that you have one type of data on one side, other type of data on another side. You find the boundary, and that will answer questions like yes on that side, no on that side. But the point is that the data which you have collected may not be directly in this particular framework. Okay, it might be more generic thing, and then a naive linear classifier will not work. And that is the place where lot of work was done to figure out how do you convert a non-trivial pattern recognition problem into this kind of situation where linear classifier will work. Okay. So, more general patterns handled by what is called a feature map. Okay. Yeah, incidentally, the leader in this particular field who did lot of the work devising various method is Vapnik. Can look up the papers if you want to go into some history of it. So, what is a feature map? Feature map takes the data from the original representation to a higher dimension space, and it is a non-linear map. So, it takes say some set of values denoted by certain coordinates in the usual vector space notation, and you construct a nonlinear function. It is the job of the machine learning algorithm to construct this particular function. Okay. I will come to that in a little while, but the point is that this is now sitting in a higher dimensional space. So, even if the original data is not nicely separated, in the higher dimensional space, it will be possible to separate it by just drawing a analog of this line, which is hyperplane. So, what you call hyperplane Of course, you do not want to go to real large number of dimension, because the computer power will be more and more with the increasing number of dimension, but you have to now figure out how can I do this particular job keeping the dimensionality under control. But just to give an example where why such thing is always possible, I can take all the set of data take each point in this whole set of however many items are there in the database and assign them to separate Cartesian basis vector. And then you can always draw a hyperplane, which rather trivial, whatever it is that you have multiple data points in some dimension depending on values, positive, negative, etc. And I can separate it by drawing some plane that all the interesting ones are on one side, the other opposite properties on the other side, because they are all individual coordinates orthogonal to each other, you can always draw a plane. But you don't want to go to as large a dimension as the number of data points. It will be requiring a huge amount of effort for analysis. But the point is that such a feature map always exists, which can construct a non-linear boundary in the original space to a linear boundary in the large space. To give another example, something which is kind of easy to see, that suppose I have two sets of data, but now one part is say inside here, the other ones are here, and the boundary looks like a circle. How do I make this boundary linear? So, kind of easy. You take the original data, which has two coordinates, x and y, and add a new coordinate, which is the radius or radius square or whatever it is, doesn't matter. And then the boundary is some appropriate value of z equal to constant. All this inside point will be small value of z, larger values of z or all the other points, and whatever is circle, now I can draw a hyperplane. So there are all kinds of tricks, and people have devised lots of different patterns as a what we call benchmarking exercise, that you made some algorithm, try it out whether it works on this particular pattern or not. If it works, then well, you have solved the problem of the feature map. Okay. Now there is one particular reason or motivation of why we want to focus on only boundaries, and that is part of our experience also, and part of how the brains or any other cognitive system has evolved in nature, that when we look at an object to identify it, we do not look at all the details of whatever are there in the image. We only somehow look at the boundary where the pattern in the data changes from one type to another. If the boundary is lost, then we have what is called camouflage. You can't see it, even if it is in front of you. And it is very practical situation. And if you look at the kind of pictures which are made by cartoonists, they don't draw all the details of the figures, they will draw a few lines. And that by looking at the few lines, I will recognize that who this person is. What are those few lines which cartoonists draw? They are just the boundaries of a certain type. And from that boundaries, our brain fills in all the other details. Okay. So that is a part of the story that you have to figure out the boundary to be able to classify the object. So this is a right. And that is an important part of this data analysis. That yes, there are lots of features in the data. You don't want to look at all the features because it will just take too long. You want to quickly identify the boundary and from that make a decision. Okay. And now, well, there are data sets available which figure out what kind of boundaries are appropriate for which particular problem. There are algorithms, routines available, and so well, they are all libraries. You can find it if you search this is a subject which is kind of exploding in interest these days. There are sample data sets which will allow you to test whether the algorithm is good or not. It has to predict the correct behavior for there. There are whole variety of algorithms, not necessarily unique. So this is a vertical. You can take them ready-made and see whether it is going to do a good job in the problem which you have it in hand. And there is a more sophisticated analysis which is labeled as support vector machine, and it does a little more than all these simple algorithm. Somehow it just maximizes the boundary interval, and it is again a well-known property in the linear algebra analysis that if you have a hyperplane, then you can still adjust its slope, which is defined by the normal to the hyperplane. So And it's kind of obvious that if you have some set of data over here and something over there, I can draw this one, I can draw something like this, which also works, but then I adjust the slope so that the minimum kind of distance, which is measured along the normal to the hyperplane, is the largest. And if I do that, it helps in separating the data more cleanly. So the larger the gap, you will identify the boundary more easily.
We have tilted the hyperplane.
Hmm?
We have tilted the hyperplane.
Yeah, you are wearing the normal. Hyperplane is defined by the normal direction to the hyperplane. It's a linear algebra, and you adjust the normal so as to maximize the distance. Okay. This is what this support vector machine does. It's a linear algebra problem. You are given a sets of data, you figure out which is the base plane, and then you adjust the normal to maximize the distance. Okay. So this is a background of what is done in all these classification problems. There is one more thing which is used, and that is, yes, you figured out this feature map, but you can still circumvent some part of the calculation, that you do not need to explicitly construct this function. You only want to find the boundary, and that can be decided without explicitly evaluating what is phi of x. Okay. And that is known as another so phi of x need not be evaluated. What you want is this object which is called kernel. So let me just call it k of two data points xi and xj. X is a whole set of variables. So yeah, I can look at this thing as whole set, which is a collection of this individual xi. And what I want is something which is in some sense a measure which takes these 2 points obtained by feature map and measure the distance between them. It can be just the Cartesian coordinate distance between them, but it can be some more complicated function also if you want. And this object is got a kernel. And what you want is, you want to only evaluate this called bilinear function. You don't want to evaluate phi xi and phi xj and then take a difference of the two. And that is possible for suitable functions that you don't evaluate them, you only evaluate the difference, and the ideal this kernel is a very simple thing. You have a binary question. It just maps into two values, plus or minus 1, plus for one class, minus 1 for the other class. Okay. Don't have to evaluate this whole thing. You are going to reduce it to just one number, and you just want to figure out whether the 2 points are on the same side or they are on opposite side. And if that is done, then the classification problem is solved. Hmm? Yes, you can define many different variety. I just gave a simple description that it can be solved by a binary analysis. If you don't want to stick to binary analysis, you want to do a more complicated analysis, it can be done, but then you have to build up all the remaining machinery that goes with it. With the binary analysis, it was a simple linear algebra problem, and that runs very well on all kind of computers, and that is what people use. If you want to use a multiple classification, well, you have to divide multiple boundaries and figure out how to deal with it. This one hyperplane is enough for the binary classification.
In last line, since kernel has only one input argument, one xi.
Two input arguments.
Last line.
No. Yeah, I should write kernel. So it's not a vector space function, it's just a scalar function. And if you can find a way to measure somehow the separation between these two by any trick, I mean, it may be as simple as a dot product, or it can be given a nonlinear form as a Gaussian around the 2 points and things like that. All kinds of things people have attempted. There is no unique answer. Whatever works is good enough, and people keep on improving various possibilities. This is also in some sense problem dependent, because which kernel is good for one problem depends on the nature of the problem in some sense. Okay, so since you asked the question, what about having multiple classes being distinguished at every step? And that is something which has a connection to the quantum algorithms, because as I have described in the previous course, that with one binary query, if you use Grover's algorithm, you can distinguish 4 objects. So then the question comes that, well, can you implement it in any of these schemes? Certainly not in linear algebra, but we will design a what you call quantum computer to do that particular job. In principle, it should be possible, but nobody has done it. Okay, so question comes about quantum extensions, and there are various places which these ideas appear. So one binary question can you make a picture for it? And certainly is possible, because you are talking about higher dimensional space, etc. And if you have 4 objects, you will have to design a tetrahedral geometry which sorts out various branches at every particular step. So all the four labels are in some sense equivalent. And there is a ready-made usage for it, which is something which I mentioned. There is a natural database in steps of 4, which is our genetic information. So if you can design something well, it has application. You will have immediately be able to do something better in dealing with genetic databases. Has anybody succeeded? That answer is not known, or rather nobody has done it. So but it's an interesting problem. So not only is theoretical possible, it has a practical application. Just somebody has to work out all the necessary ingredients which go along with it. So this is one thing which can be done. The second thing is something which people have already recognized, and there are rigorous proofs constructed to show that yes, if you find this quantum version of this problem, you can certainly do something better. And that fact is that this the type of maps which you can construct in quantum theory are more in terms of variety than what you can construct in the vector space language by this mapping of x to pi of x. And how do you construct these maps? Then it becomes basically a description of evolution of a quantum state. You start with some x, it goes to some phi of x, except that phi of x is some unitary operator acting on x. It can go into higher dimension, no problem. So you have a situation like this.
Unitary evolution can lead to higher dimension.
Yeah. The other coordinates are just assigned value to 0 and you have some off diagonal entries, it can become non-zero. That's not a problem. So why these are more powerful? It's just the statement which is buried inside all the study of quantum algorithms. If this was easy, then I would have simulated all these things on the classical machine, and there is no advantage in quantum computer at all. Won't worry about it. But the fact that the quantum evolution cannot be efficiently simulated on a classical computer, it just means that it's more powerful. And the examples of these are, well, various algorithms which we have looked at, and this is a explicit proof for what you call something which has no polynomial classical algorithm known, but an efficient quantum algorithm which is known. This is the Fourier analysis problem which is at the base of Shor's algorithm. You cannot construct a efficient classical version of it, and the problem which was given as an illustration or rather a proof that you have a classification problem which can be solved easily on a quantum computer, but it cannot be solved in any easy manner on a classical computer is a function which appears in Shor's algorithm analysis, the discrete log function. So, what I mean by phi is put it as a discrete log and it generates some pattern. Now, given that pattern, can you invert and get back to x? Well, not so easily, because no simple algorithm to invert discrete log is known. Okay. So, this is something which given as a proof that yes, a quantum version, if it is available, can do non-trivial things for this particular problem. There is yet another proof of a different type of what is possible, and that is again a demonstration of the power of the quantum data, and that is in some sense connected to the fact that when we perform measurement of a data, you lose some information, because you may have a quantum signal, you measure it, you get some eigenvalues and eigenstates, but something is lost. So, the strategy in this another example is feed quantum data into what is done in all this analysis is we are looking at databases which are actually collection of classical data. They are obtained by certain kind of measurements on whatever the experimental scenario may be, and they are set of real numbers, some values, a list of them. And now we are asking a question from those values, can I construct various kind of pattern recognition. But something which is extra is that the original data which you are trying to classify is quantum itself. You have not performed any measurement and reduce it to classical one list of values, and that means that original data has all kind of quantum correlations which are absent in the classical data after you have performed measurement. So, these are And these are all kind of correlations which are non-trivial, which have no simple explanation in the classical language. Not only that, they cannot be simulated easily in a classical pattern either. And if you are able to analyze all these quantum correlations, in some sense they are all the informations buried in the off diagonal terms or phases. And the phases are something which you will lose if you perform a measurement, but if you are there, you can do all kind of interference experiments, which is buried inside all these linear maps, but interferences can be part of the unitary operator. No problem with that. So, this correlations has been shown to reduce the classification effort exponentially. The gap between having just classical data and actually having the quantum data over the same number of objects, the effort will vary exponentially. Again, there is a so-called explicit proof. And that is given in terms of determination of the density matrix in the Pauli basis. So, if you have n qubits, the density matrix has a dimension 2 to the power n times 2 to the power n, and you want to do it classically. Well, this determination require 4 raised to n effort. How many elements are there? You have to work through them. But on the other hand, the classification effort which is required is order n. The 2 raised to n or 4 raised to n comes down to something which is just order n, and that has been explicit proof is given. In a paper, I am not writing down various references here, but I will put it in the notes that yes, you can do this construction and find out the effort required. And yeah, so for this purpose, you have to actually now find analog of this kernel. So, kernel for 2 points, which I will denote as 2 data set labels, 2 density matrices in the quantum case, and that can very easily be just be a very common function overlap of the 2 state. And well, if you are clever enough, you will be able to determine the sign of that. So, that will tell you whether the 2 sets are on one side or on opposite side, whatever. But the machinery of determining all these things is kind of well known. We have used it in a simple algorithms. You are given two states, how do you determine the overlap? A linear circuit, nothing complicated. So these are the kind of things which are possible, and well, people are still studying various scenarios in trying to extend this. They talk about, well, various quantum kernels and evaluation. For this, there is a constraint or the caveat that the so-called evaluation, which I generically write down, classically it's not a problem. You want to calculate the overlap, it will be a dot product, you can find a value for it. But this quantum measurements like this, they are all probabilistic. So you have to evaluate the same thing many times, and from that determine the expectation value. Okay. For example, if you are trying to do this, you prepare the state which corresponds to the overlap of this particular quantity, you measure it. Sometimes you will get +1, sometimes you will get -1. It's a binary measurement on the end. But then you have to do it many number of times and decide whether the expectation value has plus sign or minus sign. That means out of the many trials, how many are +1 and how many are -1, that will give you the final answer. But you need to do that thing because the results are all probabilistic. You cannot bypass this in any particular setting which involves this quantum theory test. And you have to find out the expectation value because individual trials will only give you +1 or -1. But what is the expectation value, whether it is positive or negative, can be only decided after doing many trials which will reduce the variance of whatever that you are trying to measure, and then you have sufficient faith that yes, this is a good enough result. Remember, these are probabilistic things, so there cannot be 100% guarantee. And actually, even in all the machine learning algorithms, there is never going to be any 100% guarantee. It is amounting to say that, okay, I have determined this to be the correct result up to this much tolerance level. All problems are like that. There is a finite possibility of an error, whether it is classical or quantum, because that is the situation in all this large data analysis. It should work most of the time. Sometimes it doesn't work, it fails, we know that. Okay. And well, you have to define some tolerance level to be practically applicable in a particular scenario, how much error you can tolerate.
Quantum kernel here defines a measure of separation between two data points.
Yes.
So how does the method classify? So are close points classified together? Want to say less kernel value?
Yeah, so you have to still generate this density matrix starting with some initial point and applying a suitable unitary evolution. Okay, so that is not bypass, but the point is that this density matrix is the value after the evolution. So you do a non-trivial evolution which kind of separates different density matrices on one side or the other, and then you perform a measurement.
So what does the kernel value
Kernel value is just a label, in the sense that you are asking a binary question and you only want to know whether it is in this class or that class. You are not interested in detail. It was done by drawing a boundary over here, and here you will evaluate some function, but you will then just take its sign. One sign is on one side, the other sign is on the other side. That's it.
So these evaluations of the mode density matrices, will they be different defined by the same unitary or?
No, the unitary thing will be designed. It just like here, these are so-called support vector machines. There are library programs. You will have to find a corresponding algorithm which will generate this evolution. It will be a quantum circuit, some sequence of gates, and as we have been talking, it will be reduced to 1-bit rotations and 2-bit control knots, things like that. But you have to design that particular circuit. So you take the initial data, pass it to the circuit, which will produce this, and then perform a measurement of the output of the circuit, which will tell you you are on that side or this side. So you can, well,
So we need to have a formalism for measurement also.
Hmm?
We need to have a formalism for the measurement also.
yeah. How do you perform this measurement? Well, there is a various kind of tests. This one of the circuit which I remember is something called a swap test. It goes like so let me call row 1, row 2. This is a ancilla bit which I put in a superposition using a Hadamard gate, and then use it as a control to apply this swap gate or Fredkin gate on the other two states. It means that if this particular state is 0, don't do anything. If it is 1, then exchange it. And then I will measure this thing again after inverting the superposition of the control bit, and measure this particular bit. These things are just dummy possibility which are just ignore, and then what is the expectation value of this one bit, and you work it out and you will find that it's yeah, so its expectation value is 1 plus or minus half for normalization. That is the result. You can do it with a rather straightforward circuit, and depending on the overlap, you will get sometimes plus and sometimes minus. This is the expectation value, and with enough number of measurement trials, you will know whether it is on one side or the other side. So anyway, this is not the only test. We can design many simple circuit, there is something which will do a similar job, but where you require the inverse of this function also. So, since this is a overlap, you can write the overlap in many different ways, and if you write that as a overlap of u times x1 times u times x2, etc., and the another way of writing it is a u times x1 u times x2, and this density matrix is actually the square of it. Can you measure this directly? Fine, you can take this u on the other side. So, you have to have x1, then u inverse, then u, and you measure the overlap with x2. So, this is also measurable. But to be able to measure this, you need a circuit which can implement both u and u dagger. So, I mean, these are nothing complicated. We have seen how to handle unitary operators using some logic circuits that you can implement in many different ways. The point is, this is a very simple function, and all you need to calculate is certain dot products, and you have a simple definition for it.
Because the second one doesn't extend to these states.
Hmm?
The second one
Yeah.
doesn't extend to these states.
Yeah, that is a difference. This one requires you to be able to deal with pure states. This swap test works even if this rho 1 and rho 2 are mixed states, it will still give you a result. So, there are minor differences in either dealing this directly in the vector language, or the density matrix is more general, which can be handled even in the mixed state language. So, people have done many different studies, and one of these state is how do you construct that feature map. Well, first you need to encode the data, and you have to take that classical data and convert it to a quantum label. So, many ways people do it, and one of the simplest one is take a state which is 0 to the power n and apply a Hadamard gate on everything which we know that constructs a uniform superposition of all the possibilities in the Hilbert space, and then you apply this some label as rotation parameters, where this classical values of x1, x2, x3, whatever they are all converted into some angles, and you apply that, and this is a produce a state which is some function of the classical values which you put in, but now it is described as some vector. It's not the only possibility, but something like this can be done. But it is important that if you want to study this quantum version of classification. You take that classical data and generate quantum data from it somehow or the other. So this is classical to quantum. And it's a kind of a subjective problem. There is no unique way of doing it, but somehow you have to embed the classical data back into the quantum space before you can run any of the algorithms.
If classical data have some correlation, can we convert it to quantum correlation?
Classical data, all these different xi are just a list of values. They are treated as independent. They may have some correlation, it doesn't matter, but they are treated as independent because they actually don't have any quantum correlations at all. So they may have classical correlation, but they are treated as different set of values. What you end up doing is, that I forgot to mention earlier, that in this treatment of classification, I use this word supervised machine learning. So what it does is it trains the algorithm on a subset of what is called a training data. So you choose from this huge amount of data one small set for which you know the answer. Okay. And then you train your feature maps and kernel so that that answer is reproduced on the training data. Okay. And then use whatever comes out for it, which will all become parameter in this mapping and definition of kernels, etc., for predictions on some unknown data. Okay. So of course, you can't get something out of nothing. So you need a sample where you know the answer, you make the best fit, and then after that is there, you keep on reusing that best fit for making predictions. So that is actually a part of the construction. How do you find this support vector machine? You need some training data, you figure out the best parameters, the boundary intervals, etc., and then those parameters you will use to make predictions for some unknown data. So what was done is, in this particular test, is this is fine, and then there is another circuit for the feature map, and as I described last time, that we wanted to have a map which is quite versatile to cover many of the possibilities, whether it is regular, irregular, whatever it is, and I gave a justification that the one-dimensional Heisenberg spin chain is a reasonably good model for it. So that mapping, this is one-dimensional Heisenberg spin model. So it will go like various parameters. So I was using rotation along y-axis, depending on how many of these spins you want to construct. Well, let me write one more of this. And then whole bunch of interactions which were control Z, a 2-bit and it will all be, everything will be combined together. So all 2-bit interactions will be there. The point which is useful to remember for this Heisenberg model, that all these 2-bit operators, they are diagonal, and so they commute. And so you can execute them simultaneously or in parallel or whatever it is. This one's the single bit operators, I should not have drawn a line here. They do not commute with these other ones, so they have to be applied separately. And then this is a kind of a box which is iterated for as many cycles as you want to introduce in the algorithm. Okay. So this was a repetitive process. You had so many different time steps, and every time you use this iterative structure, which is the Floquet map that I mentioned last time. 1 qubit and 2 qubit operations just keep on going for a certain number of time, and then you get at the end of it, we'll have this phi of x, whatever comes out. So these are the two ingredients. First, you have to map the data into some quantum version of x. Then you construct this unitary transformation to go into this new variables, some multidimensional vector phi of x, and after that you will perform a measurement. And it's subjective about how you measure it. You have to choose. You can make subjective choices, some overlaps, how you are going to do that calculations of finding that particular overlap from this whatever phi of x that comes out. So, this is just a setup, and now I can state the problem that we looked at, that you start from a point on the block sphere, apply this so-called chaotic evolution map, which I described last time as a Hamiltonian involving n qubits, whatever particular choices you can. So, this was a particular choice of angular momentum state, some value for j. And then tune the inverse. So, this will be the equivalent of the starting data. Okay. Take some point on the block sphere, apply the chaotic map, which was defined as in this given. I remember the notation. That you some map, you apply the operator for some particular value of j, it produces this particular state omega, which is a function of j. So, that will be the input, not this particular data. We are creating the data by some particular problem that we want to study. Then tune this part of the circuit. To find out whether you started from the northern hemisphere or from the southern hemisphere. This is the binary prediction at the end. Now, given the nature of this chaotic behavior, if you are given what I call diverging trajectories in the classical system, where given the final state, you cannot predict where you started from. It's very sensitive. But here there is a quantum version of it. It's restricted to this angular momentum states, and I want to find out whether I can find an answer, and the answer is good if you this machine learning map U produces inverse of this. Then you know where the starting point was and you have a good prediction. But given the fact that you only want a limited information, you don't have to be exact, that U does not have to exactly invert omega, even approximate inverse is fine. So, this is now the setting in which a test could be performed, and the definitions were simple enough, so that all this could be done with simple what you call simulators available with small number of qubits. You didn't have to really look for a quantum computer. The simulators, even though numerically not very efficient, will actually give you an answer whether it is good or bad in terms of everything you can count, like number of iterations. You are not talking about the computer power. And now I can give you the results, and the details are of course numerical, described by various types of figures, and I am not going to do that, but that you can find in the papers, no problem. But results are kind of simple enough to say in a straightforward language. So, the parameters which we selected because all the previous analysis is available. There was this kicked top algorithm where the strength of the kick was rotation by pi by 2. It will jump halfway across yeah. Maybe 100. This was kept fixed, that twisting parameter was taken over a large range, and these angular momentum states were chosen in this particular subset up to j equal to 3. As I have discussed last time, chaos occurs only for j greater than or equal to 1. For j equal to half, there is no chaos. Okay. So, what does the results show. This is the problem that you can do this evolution either in this quantum unitary language, or since the Hamiltonian is known, you can do the classical Hamiltonian evolution also, no problem with that. So, when the value of this kappa was small, it was able to tell me by just this Hamiltonian evolution whether the starting point was one side or the other one. But for large kappa, success rate is approximately 1. The success rate dropped to half. Half just means that I am not predicting anything in any sensible fashion. It's like a coin toss. With a binary problem, I ran the algorithm, it does not give me any information. And the whatever this is behavior was something like this, and the crossover behavior where the success rate drops to half and afterward it remains half happens to be kappa equal to 4, which is an exact answer known from lots of analysis of the classical problem. Okay. So, this is a crossover. Particular value. So, this is expected, or rather it has been repeated many times for many different people, and great detail what happens by making this evolution maps, and there are all kind of figures. So, that is fine. And then comes quantum evolution, where the algorithm was run in the exactly fashion, but now the chaotic dynamics produces the state omega as a function of g. And if I don't apply that inverse map u, just take the chaotic thing, it gives success rate equal to half. That means that the state omega jo is sufficiently random. Okay. After applying that Hamiltonian, and I cannot predict if I am just given the, I have no idea where I started with. But after tuning u, so there are various parameters. So, L is a number of these iterations. I don't know, let me see some notations. I should not confuse. There are various parameters. So there are two steps. So let me distinguish them. This circuit, I call it n time cycles. I think it's kind of flipped from whatever I have written in the paper. So let me change this value actually to be L to be consistent. How many iterations are there in that block? Then there is also how much complicated this chaotic evolution was, which is how many time steps this flow K evolution I used to produce this state omega j. So it's omega. And then number of measurements, which is to determine this overlap because it's going to be probabilistic. And we just varied all these things over a certain range, and the surprise was okay. So then because this problem was completely symmetric in the initial state, because it was this representation of angular momentum j, which is just representation half raised to power 2j, and it was all fully symmetrized states. So we didn't bother to do this complicated overlap tests, etc. Thus, the predictions, whatever it is. So just measure one of the qubits. There are so many of them. We wanted a binary answer. We said you just measure one of them and be done with it instead of trying to calculate some overlap. It was fine. And the surprise was that for all all the values of j which we tested. We didn't try very hard. These numbers were kept about 10. N, which is how complicated state we produce. There we allowed lot of freedom, that it be long evolution and complicated history, whatever got produced with that. And the success rate was certainly bigger than 90%. There is absolutely no effect when crossing this value of kappa. And that just meant that even such a crude approximation could produce a reasonably good inverse to whatever that chaotic map was. Okay. And it also showed that the map, I mean, you can create a very complicated evolution, but by just using only some 10 steps, you can invert it. You are not looking for exact inverse, approximate inverse is fine, and you can easily get that. It's a sort of independent of this value of n. You could get a good approximation, and this classical transition which was there did not show any change, it is basically just a flat curve. So, this was a kind of demonstration that the smearing of the state which is there in the quantum language, which is encoded in saying that I just want to know whether I am in southern hemisphere or northern hemisphere, and the answer is very simple, that you can backtrack. So, even when the Hamiltonian has chaotic character, you are able to find the inverse. And it's just a particular instance, but it illustrates the fact that the classical understanding of chaos is suppressed because of the smearing which is inherent in the quantum framework. Yeah, so I will stop there. Yeah.
So, was there any effect about where the initial state was on the Planck scale on the Planck successful?
Yeah, you are not interested in the details of the answer. That is the whole point of this. Is just a classification problem. You only wanted a discrete answer, and if you can get that with a reasonable good approximation, then it is good enough for the machine learning task. That is where you do not need an exact inverse of the transformation, even an approximate inverse is good enough. And the reason for it is that you are not looking for actual location, but only some distribution in some part of the space. Are you in that particular part or not? Nothing more than that.
One clarification, the circuit for the chaotic evolution and the structure and for the pitching up is the same way, except differing in the number of steps. But that is good.
Yeah, it's whatever I mentioned last time. It has its own parameters for producing this particular J. It was also made from this 1 qubit and 2 qubit kind of thing, but there were different parameters sitting inside there.
But the same structure for the chaotic evolution as well. The observation is that even
Here you are trying to find its inverse. If you want an exact inverse, it will be just the same circuit, etc. But you don't have to work so hard to get the exact inverse. Even an approximate inverse can be obtained with a far number of steps, less number of steps.